Thank you very much, Tiff, for that introduction. And like Tiff said, I am originally from Montreal, Quebec, over on the East Coast, and this is a very big honor to be speaking at UBC. I always had very mythical visions of what the West Coast was like growing up. And when I was a graduate student in Seattle, I visited Vancouver often. So this is, thank you for virtually having me. So let's begin. So what we have here is a photo of the Via Appia, which is an ancient Roman road that connects, I forget what city, to Rome. But the reason why I'm showing this image is that if you look at the title of the book, it is Statistical Inference via Data Science. In other words, it is learning statistical inference by way of data science or through data science. So I really want to emphasize that point throughout my talk. So the first thing I'm going to say is that a guiding paper that I've read that I've used as sort of just a very seminal paper that's guided my thinking in creating this project is a paper called Mere Renovation is Too Little Too Late. We Need to Rethink Our Undergraduate Curriculum from the Ground Up by George Cobb. Unfortunately passed away within the last couple of weeks. And this was a paper in the American Statistician. It was very influential, at least in the circles I run in. And there's a couple of points that he brings up. One of it is in an intro stat class, you really want to minimize prerequisites to research. Now, we don't mean research in the sense of publishing in top tier journals, but more minimizing the number of steps before students can start answering questions with data. And the other point he brings up is that with the advent of computers, we are now in a position to substitute mathematics with computation as the quote unquote engine of statistics. So instead of using asymptotic theory, we can just use repeated resampling and so on and so forth. In other words, instead of presenting students with this, we now have the option of presenting students with this as the means by which to learn statistical inference. So here is what I call my proposed path for intro stat students. And again, this is sort of a guiding principle that we had throughout the writing of this book, my co-author Chester Ismay and I. Number one, have students develop a minimally viable data science toolbox. Now, we can argue about the semantics of minimally viable and data science, but I usually think of it as rudimentary data visualization and rudimentary data wrangling. The next step in this path, build intuition for statistical inference by having students implement simulation-based methods using these tools. So whereas the idea of teaching statistics using simulation-based methods isn't all that novel, most of it has occurred through the medium of applets or apps that students had very little control in designing. But now that a lot of these data science tools have become a lot more accessible, we are now in a position to have students code this up for themselves. And then the final step in this pathway is we still need to bridge that gap between simulation-based and traditional asymptotic-based inference. So, I mean, a lot of the literature out there in the world, they still, rely on stuff like ANOVA and t-test. So I think it's important that students know what these methods are and be able to connect the dots. And it's not always obvious how to make those connections. In other words, teach data science first. In other words, teach the tools first, and then teach statistics second. So I'm not going to talk too much about the tidyverse because it sounds like there exists a course, a DSCI 100 that covers these topics. But here's just a quick summary of why I think these data science tools are useful. So chapter 3 of ModernDive talks about data visualization with ggplot2. And this is what I like to call one of these, you don't need no PhD in statistics moments, just exploratory data analysis. Is there a difference in response between these two groups? In my opinion, I would rather students be able to create such a box plot instead of just plugging the values into a stat calculator and get reporting a p-value of 0. I think exploratory data analysis goes a long way. Next on my background here. Chapter 2, 4, and 5 consist of data wrangling, importing, and the idea of tidy data. So what are sort of the major learning goals of these chapters? Have students practice looking at raw data values using the view command in RStudio, looking at data at its most granular and fundamental units. Next, the idea of functional programming with the pipe. Do this, then do that, then do this. And what this fosters is the idea of algorithmic thinking, of following a set of procedures. So for students to be able to use the simulation-based methods I'll talk about shortly, they need to get at least some practice using the pipe or thinking in terms of functional programming. And also something that's not all that obvious to people who are new to data is thinking of data in terms of tidy data frames that can be transformed. So basic manipulations to take your original data and transform them. And here's an image that I stole from Tiffany's forthcoming book. I mean, the idea of thinking of data as it's presented on the left-hand side, takes a little bit of practice. This idea of variables as vectors versus variables as lists. How can I, summarize? How can I aggregate? How can I filter out rows? So again, we're not trying to teach them to be data wrangling experts, but rather a minimally viable set of tools. And the last thing I'll talk about before I talk about statistical inference that we cover in the book is we do linear regression. So both simple linear regression and multiple linear regression, but using categorical variables. We don't ignore that. So the apex, if you will, of the linear regression chapters are, we have the students do a visual model selection. So for example, we have data here pertaining to teaching evaluations at the University of Texas, Austin. We have age on the x-axis, we have teaching score on the y-axis, and we have the colors corresponding to gender, which was recorded as a binary at the time of the study. So we can present students with such models and get them thinking about model selection. So in both cases here, we see that because the slopes are negative, as instructors differ by 1 year in age, so also does their teaching score tend to diminish. But looking at the interaction model, you can see that the score, the female instructors are penalized at a higher rate for aging. But you can contrast this to a different situation where the interaction model and the parallel slopes model are actually quite similar, as I do over here. So over here, you can get into discussions about, things like Occam's razor. Is the additional complexity of having 3 separate slopes and 3 separate intercepts, as presented on the left-hand side, merited? Perhaps you would favor the simpler model, as is the case with the parallel slopes model, which assumes a common slope for all 3 groups. So again, we don't go in depth into model selection because this is, after all, just an introductory course. But even just presenting a series of visualizations, in my opinion, can go a long way. So hey, why don't I pause and see if anybody has any immediate questions that jump out of them. Okay, unless I'm missing something. Tiff, I can't see the chat window and I don't see anything.
I'm looking at the chat window and I don't see anything. Yep. And just a reminder to folks listening in, if you do have a question, write hand in the chat and Albert or I will take a look every now and then to check for it. But I think you're good to go.
Yeah, if you could keep an eye on that, that'd be very helpful, Tiff.
Certainly.
Thank you. Okay, now that we've talked about our toolbox, let's get to the meat of this talk. Build intuition for statistical inference by having students implement simulation-based methods using these tools. Let's start with chapter 7. What proportion of this bowl's balls are red? I'm a firm believer that especially when it comes to ideas of sampling and resampling, doing things by hand goes a long way. There's so many layers of abstraction that reminding students that ultimately all of statistics is about this image. You do not have the resources to do a full census, therefore you must sample and estimate all quantities. So if you're curious to read more, I've included a link to a paper that espouses the merits of doing things by hand. So we have one of these balls, these bowls at where I'm at that have a number of red balls and a number of white balls. So we have students, take samples from this and maybe construct a histogram by hand. But here's where things get interesting. We now do the virtual analog of what we've done by hand. And we say to students, hey folks, ultimately with all these simulation-based methods is we're just mimicking what we did in real life virtually. So what we have here is a virtual representation of the 2,400 balls. You see that all the balls are either red and white. And we see that there are 2,400 rows. Well, now we need a virtual analog to the shovel. This is the repeated sample n function. Let me explain the components. You're going to take samples of size 2, but you're going to take 5 replicates of this. We're building up to the idea of repeated sampling. So take the bowl, pipe, again, functional programming, sequences, algorithmic thinking, then take 5 samples of size 2. This is that computational element I was talking about. So what we can have students now do is we're going to take virtual samples of size 50. But instead of doing it for 40 students, why don't we have them do it 1,000 times? Now, again, remember, the students have been exposed to data science, they have been exposed to the pipe, so they are able to break down what this is saying. Let's take a look at the commands. We are going to take 1,000 replicates of samples of size 50. We'll group by the replicate ID number that you can see in the top right over here, and summarize each replicate by the proportion red. And because they know ggplot, you can have them construct sampling distributions virtually like this. This is as opposed to, I shouldn't say as opposed, but this is an alternate pathway than just using the central limit theorem. They can actually see, okay, what is a sampling distribution and how it's created. So there are 2 goals of this sampling simulation that we articulate in the book. Again, we want the students to understand the effect of sampling variation, notions of standard error, notions of accuracy and precision, center, and so on and so forth, but also understand the effect of sample size on this sampling variation. So that would correspond to using different size shovels. Now you can either, if you have the luxury of having this bowl in your classroom, show them the shovels, but even just showing them the images goes a long way. And by tweaking that code, which is something they know how to do, they can construct differing sampling distributions and see that in fact, yes, the sampling distribution narrows as the sample size increases. So again, the key message here is that they can implement these ideas for themselves. Here are the various sampling scenarios that we cover in the book. Now, taking this idea and generalizing it to 4 other types of population parameters takes practice. So we see here in the first row for scenario 1, whoops, I'm sorry about that. For scenario 1, we do it for population proportions. We also do it for population means, differences, and also regression slopes. So we cover in the book all these examples here using real data and simulation resampling based methods. Let's unpack scenario number 2. Oh, I'm sorry. Before we unpack scenario number 2, I want to talk about a package that we leverage to do such resampling based methods, including the bootstrap and permutation tests. It is the infer package. The goal of the infer package is to make statistical inference tidy and transparent. And much like the dplyr package, where the function is the verb, the function names are verbs of what you want to do to your data, the same concept applies here. We have verbs like specify, hypothesize, generate, calculate, and visualize. The idea being is, starting on the left here, you take your data, you specify which variables are of interest, you set a hypothesis, you generate your replicates. For each of your, say, 1,000 replicates, you summarize them with the summary statistic, and then you visualize the resulting distribution. I think I saw a chat question pop up. Could that individual ask their question?
I think I just put a reminder in there for latecomers to ask questions in the chat. So I think that was just me posting. Sorry.
Thank you. No problem. But the nice thing is that this package is actually quite versatile. For confidence intervals, you can merely skip that step. You're going to specify the variables of interest, generate, in this case, bootstrap resampling with replacement replicates. For each one, compute the summary statistic of interest, and then visualize the distribution. And again, to be able to do this, you need basic familiarity with ggplot and dplyr. Here's an example. What is the mean year of all US pennies? Now, when it comes to mint policies, we're maybe not as forward thinking as back in Canada where they've abolished the pennies. We still use pennies, so this exercise still holds in the United States. We want to know, okay, what is the average year of all US pennies? So we gather a sample of 50 pennies. We talk about the merits of the sampling methodology. Again, we have a virtual analog. We have the 50 pennies coded up into a data frame. So using this data frame, we're going to take bootstrap resamples with replacement. Now, I have my students do this in class using slips of paper. The idea being you really want to inculcate the importance of doing it, the resampling with replacement. So using bootstrap resampling with replacement, let's use the verbs from that infer package. So again, it's the step-by-step algorithm that goes into constructing a bootstrap distribution. Let's go over the steps. Specify the response variable of interest. In this case, it is the variable year within the penny sample data frame. Next, generate 1,000 resamples of size 50. By default, the sampling here is replace equals true. So if you want to do the permutation where you're not replacing, you would have to set replace equals false. But by default, it's true. And then for each of those replicates of 50 resampled pennies, how are you going to summarize each of those resamples? Using the mean. And using that, you can construct the bootstrap distribution whose shape and spread approximates the sampling distribution. And then from there, you can say, okay, hey students, where do quote unquote most values lie? and they'll eyeball it, and they'll usually say something between 1990 and 2001. Then you can follow up and say, and talk about the idea of confidence intervals. So by having them construct this distribution by hand, they really, we've minimized the number of layers of abstraction. They can construct this distribution by hand instead of us just presenting it to them in an app, which they had no say in constructing. Pause for water. Now again, I want to emphasize in the bottom left over here that the structure of this package very much mimics dplyr. The function names are intuitive. They are verb-based, corresponding to the action you want to perform, and you build up a sequence of actions using the pipe operator. Great. Now let's do an example of hypothesis testing. Hypothesis testing now has an additional step, which is marked in H0 over here. You have to set what your hypothesis is. So for this one, we're going to use real data from the 1970s. Does gender affect whether or not you will be promoted at a bank? This was based on a psychology study done in the 1970s. Let's take a look at the data. It's a little bit involved, so I'll leave it up on the screen for a couple of seconds for you to look at. Okay, let me break down the study slowly. Researchers created 48 identical resumes and submitted them to 48 bank managers at random. So again, it's the same resume. The only thing that changed between the resumes was the gender of the name on the resume. You had a very, let's say, gender, heteronormative name that was indicating male and also female. And these are the differences in promotion rate, meaning did the bank manager based on that resume think, should I promote this individual or not? And based on, and I think there were 24 in each group, there was a difference in proportion promoted of 29.2%. That is the observed test statistic. Men got promoted at a rate 29.2% higher. Great. So again, this data is now stored in a data frame, promotions. Now I've randomized the rows because they were sorted they were prearranged. But the idea being is that the outcome variable is binary, promoted or not, and the explanatory variable, which sorts the individuals into two groups or two samples, is also binary. But here is the idea that you can inculcate into students, that assuming the null hypothesis of no difference in promotions rate. So let's say there is no such thing as gender discrimination. You tell the students that, hey, that means this variable gender is a meaningless variable of a series of meaningless labels that you can shuffle to no consequence, again, assuming the null hypothesis is true. So we all know this as the permutation test, but we're building up to a hypothesis test. So we tell the students that, again, in this hypothesized universe of no gender discrimination, let's shuffle those labels, gender, a bunch of times and create variation. So now this code, the infer code here is as follows. We now specify the variables of interest a little bit differently. We say, okay, the outcome variable is decision, meaning promoted or not, binary, and the explanatory variable, which sorts the individuals into two groups, is also binary, gender. We set a null hypothesis as independence, meaning the two groups are independent. The other way you can set a hypothesis is point hypothesis. So this would be when you have a one sample inference. But here you're saying that because we have two samples based on binary gender, you're assuming that the two groups are independent. We're going to generate 1,000 replicates, but of type permute, the idea of the shuffling. Now, I have my students do this with a deck of cards to understand that, okay, we're just taking these labels gender and randomly reassigning them to the individuals, something we can do given that the null hypothesis is true. And then last but not least, the summary statistic for each of these 1,000 replicates is the difference in proportions. Now, coding this up actually using dplyr is actually a little bit tricky. So we have a built-in function where all you do is type stat equals difference in props. So again, it's those 4 steps. What do? You create the simulation-based null distribution. They have now constructed this by hand. And you can present this to students and say, hey, where is it centered? It's centered at 0. Why is it centered at 0? You can build a narrative. You can build a story off of this visualization, which they've constructed by themselves. But then here you have the observed test statistic with the corresponding one-sided p-value shaded. So you can ask the students, okay, how plausible is our hypothesized universe of no gender discrimination, given that we observed 29.2% as the difference? So again, they've used computation rather than the 2-sample t-test formula, the mathematics, to investigate this question of whether or not discrimination exists. Now, some of the more astute individuals in the audience might have noticed, why do I have these parentheses over here? Well, it's because there's a couple of extra tweaks you need to place whenever you're using categorical data. You have to define which of your outcome variable is the success it's promoted. So notice how there you have to define an extra argument that of the decision variable, the success variable in your proportion is promoted. But then also for the calculation of the difference in proportions, you need to specify the order. It's male minus female. So I didn't show that at first because I didn't want to overwhelm everybody, but the logic is the same. It's specify, hypothesize, generate, and calculate. Now, this is not an idea that the authors of the infer package came up with on their own. There's a computer scientist by the name of Alan Downey who wrote a very seminal blog post, I think it was about 5 years ago. And he comes at all of this from a computer scientist perspective, and he argued that ultimately there is only one hypothesis test. That and it's true, every hypothesis test on Earth follows this basic flow. And if you can understand this general flow, then anything about any particular hypothesis test only becomes details. So this is, if you're looking at it, where the infer package got its inspiration from. The first thing I want to highlight is the top row. You have your data, okay? In this case, the 48 resumes. You compute your test statistic. You call that the observed effect or the observed test statistic. You mark that. But then the next step is, okay, given your model for H0, whatever that may be, you have simulated data. In a permutation test, okay, it corresponds to just reshuffling the labels. You take that simulated data, and for each instance of that simulated data, you compute the test statistic, and you compute that same test statistic you draw out the distribution. And the p-value is just whatever's more extreme. And this is so liberating in the sense that once you understand this framework, then you are empowered, if you will, to understand any, at least I should say, frequentist-based hypothesis testing procedure. And the infer package was built with this in mind. So let me rewind. The idea is the basic framework stays the same. The only thing that changes are the details that go within it. So I really like this idea. There is only one test. Okay, and the last thing that we cover in ModernDive that I'll just go over very quickly because it doesn't sound like it's of immediate concern to you folks is that after we've done sampling, hypothesis test, sampling confidence intervals and hypothesis test, we revisit regression, meaning we revisit the standard regression table output where we view our data as a sample. Now we're in a position to understand what is a standard error. We are now in a position to understand that these values correspond to a, what's it called? A hypothesis test of the slope being 0 and versus the slope not being 0. And in fact, you can do simulation-based inference for regression in the infer package as well. So for example, here is the null distribution of the slope. Last but not least, you can also do build confidence intervals via bootstrap resampling. And we see here that we have the bootstrap distribution based on, I think, 1,000 resamples from the sample of data in question. All right. So before I continue to the final step of my sort of pathway, I'm happy to open the floor to any questions, any quick questions at the moment.
If folks have a question, please place our right hand in the chat. Maybe I'll ask a question at this point, if that's okay, Albert.
Sure.
My question to you is, up until this point, so where you're trying to build intuition for statistical inference via implementing these simulation-based methods using the tools, what is the biggest sticking points for your students?
I think the biggest sticking point is there's two. Let me go back to hypothesis testing. To actually draw out this line right here takes a few additional steps. You have to compute the observed test statistics separately and then slam it into the diagram. The authors tried to figure out a way to automate that, but they couldn't figure out a good way. So there is a few steps above and beyond this code I showed here to computing this p-value here. And the other sticking point that I want to make is the leap from, where is it? Here. Yeah, so notice here, I don't use the infer package to build this sampling distribution. I use the repSampN function. So there is a little bit of work finessing you need to do to bridge the gap. I mean, the infer package actually uses the repSampN function inside the black box, but there is a little bit of work to say that, okay, now that we've seen this virtual shovel, how do we transition students from sort of a dplyr way of thinking into the infer way of thinking? So that is another sticking point that I've observed, is that this requires a little bit of finessing to jump from this very granular, low-level repeated sampling function to this infer framework.
Gotcha. Thank you very much. Matthias also has a question. Matthias, do you want to unmute yourself and ask it?
Thank you. So thank you, Albert, for your presentation so far. Very interesting. The one question that I have is it's a bit more sort of, it's not about the details per se. It's how do you convey to the students, or to what extent do you convey to the students the limits of so when would this not be appropriate to, like, it to use. It seems to me, I'm always worried that the students might leave with the impression that, hey, I can do this whenever, you know, there is no assumptions, there's nothing I should worry about, right? So
Absolutely.
to what extent, or how do you, is that part of your, anyway, are you going to touch upon that? Maybe you're going to touch upon that later, but I just didn't want to forget about it.
I'll touch about that right now. I think that, again, and it is something that I'm going to touch about in my third bullet point in my pathway, is that there's an inherent assumption to how ModernDive is written, is that it's all jammed into a single semester. So that transition away from two, how about this? One thing you could do as an assignment would be, okay, maybe you have the students do the bootstrap, you know, resampling with a very small sample size, where a situation where the empirical distribution is just way off the true distribution. That would be one example of something that you can do. Or another example, given this thing here, is maybe you could have them do, the sampling where the proportion P, you know, the conditions for the central limit theorem to hold for proportions don't hold. So maybe your true proportion P marked in red is either very close to 0 or 1. So in my course, unfortunately, I don't have the time to just completely exhaust everything, but the framework to have students, quote unquote, hit the wall is definitely in place. So, you know, like that would be a good example here. Like, let's say the true population proportion was very close to 0 and your sample size is very small. Then you could show the students that, hey, you know what? The sampling distribution there is actually going to be very skewed. So I think that so to answer your question, Matthias, I think the possibilities are there to have students, you know, hit the wall themselves. But unfortunately, in this textbook, we spent so much time covering the data science and the regression that we just don't have time to cover everything.
Great, thanks.
And I see one more hand up from Gabby. Gabby, do you want to unmute yourself and ask your question?
Yes, thank you. Thank you, Albert, also for sharing this material with us. My question is about the difference between sampling from a population and sampling from the sample. I've noticed that my students get very confused when I present these two things. They can understand the difference between, okay, is this the central limit theorem? Is it bootstrapping? What is the relation between both? And they at the end of the day, what I notice is they don't understand where they're sampling from.
Yeah. That is a huge sticking point. I wish I had a silver bullet that you could just say to students and they would understand that chapter 7 is based on a simulation that you would not do in real life. You know, you would not take repeated samples. Whereas in once you start going into resampling from a single sample, as you say, you only have one sample. I think that this is something that is not something that technology can solve. For example, what I do to emphasize that point is I actually show them this sample of 50 pennies. And I say, okay, folks, now this is what we're going to do that's no longer a simulation, but what are we going to do in real life? How are we going to create sampling variation using this single sample of 50 pennies? So that's one thing that I think, again, maybe I'm a little pessimistic. I don't think technology can solve. It's really, we have to repeat that sampling from a population, or I should say resampling from a sample, is an analog to sampling from the population. I unfortunately don't have anything better than that.
Thank you.
Okay, so there's one more question from Bruce Albert, but he said he can also wait to the end. Do you want to, I don't know how much material you have left to present, and I want to make sure we have time for that.
Let's put Bruce first in the questions, just to make sure I can lock this down.
Okay.
How does that sound?
Bruce, please unmute yourself and ask your question.
Okay, thank you. Thank you very much, Albert, for your interesting presentation so far. And I'm a big fan of simulation-based inference for getting students to grapple with these difficult ideas in inference. Looking at it from a kind of cognitive psychology perspective, historically when we taught inference, we loaded the students up with a load of math, and the students did math stuff, which they typically didn't really understand, and that didn't lead them to what we were really aiming for, which was the understanding of inference. And my concern is that we're replacing that with a load of R stuff, which also they might struggle to understand, and maybe to hold ton of use for them going forward, or although maybe it could be if they really grasped it. Do you see that being a problem? So I suppose the bottom line is, when it comes to like measures of how well students understand inferential ideas, research of Nathan Tintle, for example, which I'm sure you're familiar with, suggests that they do a bit better.
Slightly better, yeah.
They do a bit better, but they're not knocking anything out of the park.
No,
they do a little bit better, but
no.
I mean, my guess is, do we need a combination of a whole load of different things? Physical, move to these applets, and then move to perhaps something like you're showing.
That is an absolutely excellent point. I think that, I've read some of the Tintle's work where they've actually tried to control for a bunch of factors. I think there was one where they actually did an experiment and they showed that the understanding was marginally better using simulation-based inference. The way I see it is that, in a certain sense, I may be a little pessimistic. For students to really come out of a single course and getting it all is just not going to happen. And if you have to choose, okay, we can either confuse them with the asymptotics, or we can confuse them with the code. Hey, at least they'll get some coding techniques out of that latter approach, again, which is based on simulation-based inference, which is shown to be, from the few studies that I've seen, marginally better in terms of student comprehension. But that does build to my third point in this talk here, and maybe I'll answer your question fully when I talk about this third element right here.
Thank you.
So actually, I think we're perfect on timing. I don't have that many more slides left. So the last thing is, and the idea of bridging the gap between simulation-based inference and traditional asymptotic-based inference. So to follow up on Bruce's question, maybe you can think of this as bridging the gap as seeing the same idea again. Therefore, this is an opportunity to concretize these ideas and get that practice and that repetition that you truly need to understand these concepts. So this is what I tell people typically, because again, this book was written under the constraints of an assumption of this being a single course. If you only have a single semester or whatever to teach this, I always tell people, drop probability theory. Drop the combinatorics, drop the binomial theorem. Again, drop the asymptotic theory in favor of simulation-based inference. Introduce this, there is only one test framework, and tell students that this is the case. Again, that the idea of generalization after they've seen some examples can go a long way. And last but not least, de-emphasize chi-square tests in ANOVA. There just isn't room to do everything in a single semester. But here's where I think that you folks are in a very, very interesting position, given my understanding of your sequence. You folks are in a position when you have room for data science. That completely changes the calculus. Meaning, if you can assume the students have done data science in a separate course as part of a multi-sequence sequence of courses, then you have the luxury of, really hitting these points. So instead of dropping probability theory, cover probability theory. In particular, the idea of, a CDF or a probability mass distribution, and the idea of z-scores and normalization. We don't have time to cover that in ModernDive because the assumption is you're going to use it in a single semester. But if you now have that luxury, you can spend times on this. Next, drop asymptotic theory in favor of simulation-based inference. Make explicit connections between the two. For example, if you have the luxury and you've had time to talk about power, you could make the argument that, these simulation-based methods actually have lower power than asymptotic-based methods if the conditions are met. introduce there is the only one test framework and tell students it's true. Repeatedly go through that framework and convince students it's true. You can tell students that all you want, but if you can have them in a problem set or an exam, just say and see for themselves, oh wow, this is all just the same thing over and over again, then they'll convince themselves this is true. And one way to do that is, instead of de-emphasizing chi-square tests and ANOVA, cover chi-square tests and ANOVA as case studies. I would love to be able to one day, just after they've gone through all the simulation-based inference, after they've gone through this there is only one test framework, throw that problem at them and see if they can map to all the elements of there is the only one test framework. Currently, this is the state of ModernDive about number 3, that bridging the gap. There's an unspoken assumption of use in a single term course. Thus, a lot of the material that bridges the gap between simulation-based inference and traditional inference, I mean, just look at the section numbers: 7.5, 8.7, 9.6, 10.5. They're basically relegated to the conclusions of the chapters that I've noticed students don't read anyways. And we just don't have time to cover them. So, we do things like, okay, folks, hey, look at the formula down here and compare the formula to what you computed using the computer. We've done things like superimpose t-distributions on top of null distributions and resampling and bootstrap distributions, but you really have to go through the procedures of going on pen and paper and doing these problems out for that to stick. I mean, you can show and tell students this all you want, but unless you have the luxury of assigning these as problems, the retention is just not going to be there. So to go back to your point, Bruce, maybe this is where that or maybe this is where things can be as good as they get in a single sequence in terms of getting that retention. So oh yes, and note here that I put a link to literature. This can definitely be improved. ModernDive does not do this enough. But the way it is right now, we just don't have time. That's why when Tiffany explained to me my understanding of what it is that you folks want to do, I'm very, very curious. Again, after they've developed that toolbox, after they've built that intuition for simulation-based inference, which I think is a lot more intuitive than asymptotics. Then, if you can bridge that gap, I'm just so curious to see how the students assess and whether or not that true retention takes place, and the students are able to, pick up a psychology paper or pick up a bio paper and understand truly what all inference-based results are actually trying to say. So to conclude, I just want to note that, hey, we spent a lot of time picking out that image on the cover. That took a lot. We thought very carefully. The idea of sampling from a population, that's what inference is about. You can find this online for free at moderndive.com. If you're interested in purchasing a print copy, you can buy it at the CRC Press website. There's a discount code there that I think takes off 15 or 20%. And once again, the slides for this talk are available on Twitter at twitter.com/rudeboybert. Thank you very much.
Thank you so much, Albert, for a wonderful talk. I'm going to invite everybody to unmute themselves and give him a warm round of applause for the talk, and then we'll ask questions. Okay, so we have 7 minutes left for questions. So if you do have a question, please write hand in the chat. And then, I don't know, Albert, if you want to stop sharing and if that might be easier for you to also see the questions. I can call it the questions, but I guess maybe we could go to gallery mode. If people are asking a question, maybe you want to turn your video on. I'll turn mine on now. So it seems like we're interacting, if it's possible and comfortable for you. So in the chat, I see that another hand from Matthias. Matthias, please unmute yourself and ask your question.
Sure, thank you. So thank you, Albert, again. It was a very motivating thought. And I have to say that I agree with everything you said. I have a more than a question, is maybe just picking your brain or your experience in the following sense. I completely agree, and I couldn't be happier when I saw your slide that says ditch all probability as your first bullet there in a one semester course. And the problem that I've had when I try to do that in one of our intro courses is to do that. It's like, forget about counting how many balls you can get from this urn and so on. And even in your last suggestion there, to dump, to ignore all the chi-square and ANOVA test, at least at the beginning, is when you deal with service courses that are taken by students from other disciplines. That's what they want. They want the t-test. And whereas to me, and this is my own personal point of view, our students should see the t-test in their fourth year at the end of it, right? Like a one specific, oh, here's a particular case with a formula, who cares? But it seems to be that at least in this university, we have to give them that at the beginning. Is this course that you have in mind like an intro for discipline-specific students? Would it work for a service course? Like, I'm thinking, medical students or biology students. Anyway, any thoughts on that?
Now, just for context, are you talking specifically about the combinatorics-based probability, or are you talking about t-test? What's sort of the bigger thing that's on your mind?
Both. I mean, I love that slide before you started putting all the red things on top.
This is a this is a tricky thing. It's a push and pull of the way we want to do things. We know this is our bread and butter, but then, as you say, there are downstream consequences. So right now, let me go to the t-test. I mean, I try to, tell them, oh, hey folks, this is a t-test, this is a t-test, this is a t-test. And I tell them that when you encounter this later, the interpretation is the same. Maybe you won't know the mechanics of doing it. It's not ideal, but that's sort of all I can do given the constraint of the semester, is that I can at least tell them what it is. And again, this is where we stopped. I would love to know if there's sort of a minimally viable set of 2 lectures you could do to build that bridge between the two. And if anybody has ideas, I'd love to hear them. And then to go back to your point about the combinatorics probability, that I have not encountered so much as a problem for downstream courses. It's really just the methodology that they would use in papers like ANOVA. I mean, me, I'm regression, right? I mean, the statisticians, we just use regression, right? But there's a lot of fields out there that still use ANOVA. So I have to at least tell them what it is, but I don't have a satisfying answer to your question, unfortunately.
Thank you. That was. I think we're in agreement, but there's no easy way out of the current.
No, there's not.
Yeah, thank you.
Thank you, Matthias. The next person with their question up is Jim. And just a reminder that we're just a couple minutes from the top of the hour, and sadly, I'm going to need to take my Zoom room back. And also Albert will need to, I don't want to keep him over our requested time for him. So please go ahead, Jim.
I'm happy to stay if you can give me control.
Okay, that sounds good.
So my question is a simple one, and that is, can you use your pipeline, which starts with the data and involves all the simulation, can you use that same pipeline to get to Bayesian statistics where there is no sample space and no repeated sampling?
No, this is inherently a frequentist package, given that the reality is that many intro stats courses across, at least that I've ever encountered, are still frequentist based. I think that there is an initiative out there to do a Bayesian equivalent, and the name is really easy to remember. Just put a B in front of infer. So let me type it out in the chat. It's called the BinFer package. There is an initiative to do a Bayesian analog. I don't see how that would work. I don't immediately understand. I mean, because inherently there's the resampling that's inherent in infer, but there are initiatives to do something. Again, the idea of functional programming and the idea of communicating algorithmic thinking for Bayesian inference, yes. But no, we do not cover that.
Thank you, Jim. The next question is from Bruce. Bruce, please unmute yourself.
Hello again. Yes, thank you. I have a dream, and I've been working a little bit with high school students, or trying to. Wouldn't it be wonderful if, grasping simulation-based inference, if students were confronted with a circumstance that is not like something they've already seen? So, for example, ANOVA might be useful, right? So they've done a project, the data might, but they've never been taught ANOVA. And they think, well, hey, I could come up with a test statistic. I could come up with a statistic.
Oh, yeah.
They would never come up with the ANOVA test statistic, right? Nobody's ever going to dream that up. But they come up with something, maximum of the biggest difference or something. And they do an SBI based on that. Have you ever seen that happen? Or something
I
like
mean,
that?
there was talk here. That is a wonderful idea over here. So let me show this slide right here. Where is it? You see how we have difference in props over there? If students could program their own summary statistic function and to see if they could invent something that resembles the F statistic, that resembles the T statistic. And you can do that if you switch out calculate with summarize. So the nice thing about this pipeline is that it interchanges with dplyr. It all uses dplyr. So if I had time, that would be an amazing project where, let me stop sharing, where you have the students, you set the goals, you want some notion of what your test statistic you want to measure, and see if they can come up with it on their own first, and then drop the F statistic on them. It would make so much more sense than just saying, oh, here's the formula. Yeah. That would be an amazing project. Oh, I would love to do that, but the reality of where I teach and the courses just doesn't allow for it right now.
Yeah, thank you.
So,
Okay,
sounds like you gotta go. So,
oh, that's okay. I'll hang on for a few more minutes. Will's question is next. Will, do you want to unmute yourself?
Oh, hello. Can you hear me, Albert?
yeah.
Oh. So that's a very nice talk. Congratulations. Very, very clear. So you had a little example earlier on with the interaction between age and gender. And that's a sort of an interesting application or example, because it's very simple, but can you actually tackle that through simulation?
Yes. You know what you do to show this is that, you know what? No, unfortunately not. I think that the infer package currently only works for simple linear regression. Right. I don't think that it has the functionality to include an interaction term. But you can imagine how if you put a little work into the programming, you could, simulate the interaction term and see whether or not the confidence interval includes 0. So no, I think infer is currently limited to simple linear regression. Yeah,
I'm just wondering whether it's more than a programming problem, because simulating the interaction in the presence of non-null age and gender effects is not that straightforward.
Oh yeah, you're right. Yeah, no, I can see what you're saying. It's not just a matter of resampling. Well, you could do bootstrap resampling. You couldn't do permutations. I feel like again, forgive me if I'm making no sense. I feel like you could resample the observations with replacement and construct a confidence interval, but I don't think a permutation method like that is so straightforward.
So that's a work in progress, basically.
Yeah, I'd have to think about it more than.
Yeah. Okay, thank you.
Seconds.
Yeah. A very nice talk. Thank you so much.
Thank you very much.
Okay, next hand is oh, actually, I think that is the end of the hands here, folks. Does anyone have any last questions? Or if that's it, we will applaud Albert again.
Thank you very much, folks. It's been an absolute honor to be presenting to you. I hold UBC data science and stats and stat 4.5. I've been along with an enthusiast of 545. It's just an absolute honor and privilege to speak to you folks. So thank you for inviting me.
Thank you so much, Albert. That was a really wonderful and inspiring talk, and has given at least me, and it sounds like others, a lot of food for thought and ideas for our course development going further. So thank you again. And I welcome everyone to unmute themselves and give him a big round of applause before we sign off.